Our speaker today, Ron Baraze, began working at Lockheed during his sophomore year at Gunn High School in Palo Alto and was hired full-time after completing college at UCSC. He has worked on 23 spaceflight projects for Lockheed Martin, partnered with higher learning institutions such as Stanford University, Oxford Physics Department, University of Huntsville, and the Enrico Fermi
So my name
Institute.
is Ronald Baraze. I'm going to talk about the technology of space. Just a little bit of background. Um, I essentially started back in 1984. On my 16th birthday, I started working at Lockheed Martin at Gunn High School in Palo Alto. Using with our We have a program, and they still have it in Palo Alto now, which is called exploratory experience, where you can state you want to work in some field. I wanted to work in computer science, but chemistry, law, whatever. They would match you with a local company, and you would essentially work for 60 hours at that company. And at the end of that 60 hours, if you and the company liked one another, you would continue with the school district as your subcontractor through the end of your the summer after actually your senior year. And then I continued as a temporary worker while I went to UC Santa Cruz at Lockheed Martin, and then was hired 1 week out of college in 1990. And ever since then, I've been working on embedded software projects for spaceflight. I've worked on 16 different types of spaceflight projects. We've had a total of 25 launches. Some of those had multiple units. So that's my background. So the most recent project I've worked with is the GOES series. The GOES series has been going on since the 1950s. It's essentially the weather satellites. So it's for NOAA and the National Weather Service. Back in the 1950s, they actually, when they launched the satellites and didn't have digital ways of sending the data down, they actually took physical pictures and dropped them down into the ocean, where they were recovered and then became the national news. Ever since about the 1970s, we've had digital cameras and ways to get more data, and each of the GOES series has gotten more and more advanced. GOES R through U, which the last one we launched in June of 2024, is the latest and the last of the GOES series. We've switched to a new series called GeoXO, and we've actually won that earlier this year. So we will continue providing data, both the satellites and the instrumentation, for the National Weather Service. But for the GOES R versus U series, Lockheed Martin built 2 of the 7 instruments that are on these satellites, and the 4 satellites themselves were built by the Denver group of Lockheed Martin. The 2 instruments that I'll be talking about here is GLM, which is a geostationary lightning mapper. We usually, for these type of things, partner with a local university. In this case, it was the University of Alabama at Huntsville. They actually have the largest ground-based lightning detection array in the middle of Tornado Alley. And SUVI is a solar ultraviolet imager of the sun. So I will show you a number of pictures of CME flares and other data that's coming in. But about 20% of all Earth's weather is due to solar effects, not just effects of the Earth itself, or heating and other side effects that occur. One of the main reasons that we do this is there have been many multi-billion-dollar weather and climate disasters. This is just the list for 2024. Obviously, 2025 hasn't ended, so we don't have it. But there have been 24 of them that have cost more than $1 billion in 2024. So that's one of the main reasons we do this. We can detect not only the tornadoes and the storms, the hurricanes that come through, but also major fires, wind and snow events, etc., as you can see on the diagram here. So for the lightning mapper, lightning itself is, yes, interesting, but the primary reason we do it is because it is a prediction of where tornadoes are going to uh, occur. Before 2016, when we launched the first one of these tornado predictions in, for example, Texas, were, well, 23 years ago, the weather was like, a tornado came down before, so we're going to issue a warning. Well, they were wrong about 95% of the time. People ignored tornado warnings. So we determined from two early instruments that were put out by the University of Huntsville back in the late 70s and 80s that, as you can see on the left-hand side graph, if about an hour before a tornado touches down, there's approximately 20 lightning flashes per minute. That increases, as you can see, about 40 and 20 minutes before. Somewhere between about 15 to 8, you get to a peak. So instead of 20 flashes, you're above 80 flashes. And then there's a very sharp drop. And that's when the tornado begins forming, and then it touches down at time 0. Now, the IC versus CG, or the IC plus CG, that's intercloud versus cloud to ground lightning. From space, we can see the intercloud lightning, which actually happens at the tops of clouds. From the ground, which would just be the blue graph at the bottom, cloud to ground lightning, you can't see that through the clouds. The clouds act as a barrier. So if you're just looking at cloud to ground lightning, you're not actually able to see the same formations we can see through space. So that was one of the reasons that NOAA decided to put our instrument onto the most recent set of GOES satellites. With this data, we can actually approximately 15 minutes before where that peak is, give a 90% accurate notification that a tornado is going to touch down in a given 8 kilometer by 8 kilometer area. And about 5 to 8 minutes before, we can improve that to 99% or cancel a warning if it turns out we're in the 9% that's there. So our tornado warnings are significantly more accurate since the first launch in 2016, and we will this instrumentation, these particular satellites will continue until 2032, when the first of the GeoXO satellites is going to replace it. On the right-hand side at the top, you can see what the tornado risk map is, and the shaded areas, the ones that are shaded in gray, are actually special wind zones that can cause other side effects beyond the tornadoes themselves. And the bottom picture is just, you can see both the funnel cloud and the lightning strike occurring. So that's the main reason that our lightning mapper has been included in the previous and upcoming future missions. This is a 2.5-day storm, which happened in 2017, one of the first major storms. This actually crossed 20 states. And of those 20 states, 10 of them had tornado touchdowns. So this is what we're actually seeing across the day to night cycles. This is sped up 6,000 times real time. So I'll let it run to the end and let it run one more time so you can see the entire storm that occurred. But this caused 60 different tornado touchdowns. Some were, one of them was EF4, 2 of them were EF3, and then there were a number of EF2 and below, and I'll show you that on the next slide. But this is what we can see from space, from the lightning, which mostly occurs on top of clouds. Only about 10% of the lightning actually goes cloud to ground. 90% of it happens either intercloud or between one cloud and the next. So this is from Wikipedia, the list of all the tornadoes that touched down during that 2.5-day storm. The F4 is the one with the on the left-hand side in orange, and that tornado unfortunately caused 2 deaths. Then there were 2 EF3s, one EF3, which also caused 2 deaths, and then one on the right-hand side, which was an EF2 that caused 1 death. So, so we're trying to, with accurate warning, significantly reduce the number of deaths. Unfortunately, there's nothing we can do to prevent the tornadoes themselves, but if we can warn people in enough time that they can take shelter or get out of the area, that's our goal. So this was what NOAA released on the GOES right after the GOES 19 launch. Um, so this was the launch itself, and I have better video of that coming up here. But this is the graphical representation of GLM, and these are the storms that occurred around Florida, including two of the major ones, which we'll see in more detail. There's the hurricane event that hit last year. And the blue dots are the lightning activity, which has happened around the storm. A lot of it is centered on the eye of the storm, but all of the other, you can see the flashes now. They went from blue to white as they go in. But this is Hurricane Helene that went in and caused major rain events, did significant damage to Florida. As the storm passed, it also caused approximately 20 tornadoes as secondary side effects from the hurricane. Now, one of the advantages is flights can be diverted. You can see that they're specifically missing, well, in most cases, the lightning that's going in because they can get very accurate lightning data and stay away from it. You can see the significant lightning that's happening at the eye of the hurricane here. And these are the rain bands. So there's other instrumentation of the, as I said, we only built two of those. The red areas are the tornado warnings that were issued. But this comes from the main instrument, which is the Advanced Baseline Imager. That's what produces the pictures of the clouds and where the rain bands are. So that combined with our lightning data and the data from the other instrumentation gives much better warnings than we've ever had before for hurricanes and tornadoes. GLM is also wound up in the Guinness, the Guinness Book of World Records for both the longest reported duration of a single lightning flash. This goes from cloud to cloud to cloud to cloud, and reported distance. The longest duration was 17.10 seconds, as you can see, going from Argentina across Uruguay. And the longest distance was going from Texas across Louisiana. Excuse me. Let me just take a drink. Louisiana to Mississippi, which was 477 miles or 768 kilometers. The World Meteorological Organization is the one who actually goes in and determines whether these records are correct. But this never touched the ground. It just went from cloud to cloud to cloud, both of these, all the way across the two respective zones. So this is our other instrument, SUVI. It performs solar observations in the ultraviolet bands. So you're looking at one of the 6 frequencies over a 3-month period of time as the sun rotates. And so we are the instrument is sitting in Earth orbit, and so these are the views from Earth orbit for SUVI in this particular band, which I believe was the 195. Yeah, it was the 195 angstrom band. These are the different bandwidths that we can look at, and so you can see this is exactly the same time period, one fixed picture, and you can see how different the sun looks in each one of these bands. Some are specifically aimed at looking at iron. Some are are specifically looking at coronal mass ejections and such. So each of the bands has a unique scientific purpose, and that's why these particular bands were chosen. So this is what a flash looks like. On the left-hand side, you can see the flash heading off to the side. On the right-hand side, that's a flash pointed right toward us. Of course, you can't actually see all the material being released. So we provided both the side view of it and the front view of the effects. But these, as you can see, were two slightly different dates. I think they're about a month apart. Yep. So this is one of the things we're also looking for, because this can affect satellites in orbit. It can affect power stations on the sunny side of the Earth. It can, if their flare is strong enough, it can actually knock out transformers on the ground, both the local ones that are on the streets and the major transformers that are sitting in power stations could be knocked out depending how big the flare is. So this is one of the reasons that this is included as well, along with the coronal mass ejections cause the northern and southern lights as they bend around the bow shock that's around the Earth, which is essentially the Earth's magnetic field. It's compressed on the solar side and expanded on the tail behind. Do I have a picture of that? I think my first slide, actually, let me just go back to the first slide because I don't think I brought another picture out here. Where is it here? I thought it was on this slide, but it's not. Oh, it's right here. So this picture on the left-hand side, obviously the size of the Earth to the size of the Sun is approximately correct in this picture, but the distance between them is about 1,000 times shorter in this picture than there. But primarily, if the Earth puts out a coronal mass ejection and the solar wind, the Earth's magnetic fields, they're compressed on the Sun's side, but a strong enough flare can get through and come either near the North Pole or the South Pole and make the northern and southern lights through this gap essentially that we have in the Earth's magnetic field. Go back to where we were. So this is a picture of the actual GOES-R satellite. You can see how big it is versus the humans that are standing behind it. To transport this, we actually assemble it near the Cape. There's a Lockheed Martin facility called Astrotech that's at that location. We do our final transport to that Astrotech facility and put it inside essentially this nose cone that's going to go on top of, in our case, a SpaceX rocket. This is approximately 30 meters. I mean, you can see the size of a 18-wheeler versus the total size of the fairing that goes on here. There's a special road that's approximately 12 miles long that goes between Astrotech and the Cape. There's no power lines, no trees that run above it, no overpasses. Whenever they need to do a transport, they obviously close the road, and you can see the police escort in the background to move something this big from Astrotech to the Cape. So that item that you saw on the truck is this piece up here, the very top of the rocket that's on the left, and you can see the rest of the rocket along with, there's two big boosters. Now this is the Falcon Heavy as opposed to the regular Falcon that you normally see on the news. Falcon Heavies are only used for very large payloads. The ones that Musk is currently testing in Texas are the Super Heavy. That's the one that's intended to actually bring people to the moon and Mars. So far, there hasn't been a successful flight of those. But this was actually the second use that NASA has done on the Falcon Heavy. This is on the right-hand side upper. That's the NASA building, which is used to assemble and bring out those rockets. It's approximately 120 meters high, and there's a track that runs on this door on the right-hand side can open up, and there's a track that allows the rockets to move very slowly, about a quarter mile an hour, between this building and one of the, I think there's 24 different launch pads. Let's see. So this is a picture of the Cape. We went out to the Banana Creek launch viewing area at Kennedy Space Center to view it. The rocket is the tiny thing off in the distance here, but we were at Launch Complex 39A was where the launch is, and we were sitting in Banana Creek here. The two booster landings are going to happen at the two southernmost areas of the Cape. This is not doing the chopsticks catch that you may have seen on the news. These have to land on land, and they can't land on a barge with the Falcon Heavy. They're too big; they would tip over the barge if they landed out here. And I will show you video both of the launch and the boost back burns and the landing that happened last year. They did, by the way, tell us once we were out here and seated that when they started filling the rocket and getting ready to launch it, that this is a dangerous operation out here. We're about 3.5 miles away. They said the explosion radius is about 3 miles, and but the shrapnel radius is about 4 miles. So if there's an explosion, well, we're pretty much dead. So there was still only about a 30% chance that we would launch on the launch day. And these are the storms that are actually seen by the counterpart that was up there, GOES 16, at the time as we were ready to launch GOES 19. And this storm in the middle was the primary one that they were worried about was going to hit the Cape. About 10 minutes after the initial filling window, they said, no, this would go slightly south of the Cape. And so they were able to start filling about 10 minutes after the fact, and they were actually ready to launch 10 minutes after the window opened. Now, with these launch windows, they actually have to close all of the local airports, which includes, for example, Orlando, even though Orlando's approximately over here, and the Melbourne airport, which is approximately down here, because things come off the rocket intentionally and sometimes unintentionally. They want to make sure that doesn't hit any passenger planes. So they also have to close all the harbors, pretty much from about here all the way down to Miami, just in case, again, there's any problems there. And they usually close the beaches because they don't want people to accidentally get hit with anything. So just a note, after the launch itself, the cloud that was created because of the launch was actually seen by our in-flight GOES 16. So this cloud right here is actually created by the GOES 19 launch as seen by GOES 16. Excuse me. This is the launch itself. Now, there's actually a 9.5-minute video you can see on YouTube. I'm just going to show you pieces of it. So this is the launch itself. And no, that bird did not actually fly through the rocket exhaust. So there were cameras both on the ground and on the rocket itself. And you'll see much more of those, especially on the next video, which is going to be the booster separation. So there are 9 engines on the main unit and 9 engines on each of the boosters. So you've actually got 27 engines running at that point. So we're now about 2.5 minutes in. This is going to be the booster separation. So the main rocket is the one heading off the bottom of the screen, and the two boosters are the ones on the side. So this is the first of three burns. So these are the first of the braking burns before the boosters are actually going to land. So this is back to the main unit. You're looking down on the first stage from the second stage. This tube is between the first and the second stage. It's going to fall away as the first stage finishes, and then the second stage will ignite. And when it ignites, it destroys the camera we were looking at, which is why the left-hand image went away. So there are two cameras on this. That's why the Earth keeps moving. You're looking at the camera on the left side and the camera on the right side. And the second engine, which is the vacuum engine, actually burning at this point. And this is we're now 7.5 minutes in. This is where the two boosters are going to land. If you watch the left side of the screen. And so this will continue for a while. Now, one of the main things is you cannot burn the engines as you cross over another continent. We actually have requirements that say we have to turn off all engines within 100 kilometers of approaching another continent, and then it will obviously fall for a period of time, and then you can't turn them on again until you get to 100 kilometers on the other side. That's simply so people know that it's a rocket launch and not a missile attack. So this is 4.5 hours later. This is where the separation of our satellite has occurred from the second stage. You can see how far away from the Earth we got in 4.5 hours. So we're 18,000 miles up at this point. We need to get to 22,000 miles up to geo orbit. And on our own, without the powerful rockets behind us, it will take another 2.5 weeks and another 6 satellite burns to get the remaining 4,000 miles up. But at that point, we will be in geostationary orbit, which essentially means we will be rotating at the same speed that the Earth is rotating, and within 100 kilometers daily variance or so, we will pretty much be looking at the same point on the Earth. Every day there needs to be a momentum adjust performed, so we essentially stay on target and don't drift off of what we're supposed to be looking at. And we'll be doing this all the way again until its replacement. This particular one probably will be replaced in 2034, and we launch in 2024. So we've got a 10-year mission to continue until its replacements are ready. White Sands, New Mexico is where the ground receiving antennas are. This is simply a pretty picture of lightning over White Sands, New Mexico. And for most people don't actually know that volcanoes actually create upside down lightning. So it actually starts from the ground and goes upward. We, unfortunately, with GLM can't see that. We can see through water vapor in the frequencies we're looking at, which is 777.4 nanometers. But unfortunately, volcanic ash stops us from seeing these pretty pictures. But here's a nice ground picture from the USGS. So that's all that I was planning on talking about initially on the GOES projects. If you have any questions, just let us know, and when we get to the Q&A section, we can come back if you have any particular questions on that. This was another project that, many people worked on from 1964, which was before I was born, all the way through 2005, which was called Gravity Probe B. This actually was a project to measure Einstein's theory of general relativity, both the geodetic effect and the frame dragging. Those are the two equations that are on the bottom of the right-hand picture. It was done as a collaboration between Lockheed Martin and Stanford University in Palo Alto with NASA funding to both build the instrument and the satellite simultaneously. It took 40 years to develop. 1,700 people worked on the project, including 1,000 university students. It ran for 18 months on orbit and then took another 6 years to analyze the data. I believe the final report came out in 2011 after it had gone through all the various systems. There was 110 PhDs that occurred from the various students that occurred because they were working on Gravity Probe B. And one of the side effects was the aircraft foul weather landing system that's actually currently in use was developed as a side effect of technologies that were used to create Gravity Probe B here. And it does confirm, after all the data analysis was complete, within 0.5% accuracy, that both the geodetic precision and the frame dragging was as accurate as Einstein predicted. Another project that I worked on in the late 90s was the High Resolution Dynamics Limb Sounder. This was actually an international project. So NASA partnered up with the University of Colorado in Denver, and ESA, the European Space Agency, partnered up with Oxford University. Lockheed Martin actually made the instrument itself, and worked with both of our partners. The idea was we had 21 sensors inside that top area that you're seeing to measure gas and vapor in the lower stratosphere. And the way that it actually worked is we looked at the back end of the satellite and scanned with deep space as the reference, and then kept scanning down every half kilometer, essentially peeling the Earth's atmosphere away like an onion. And so with obviously the appropriate mathematical connections, as you scan to the first half kilometer, that gave you had deep space as a reference. Then you would scan in. Then when you went down another half kilometer, you have to subtract the appropriate amount of what you saw then. And we kept going down until you hit the Earth's surface and then scan back up. So we were looking for nitrogen dioxide, water vapors, chlorofluorocarbons, nitric acid, aerosols, etc. As over a 3 and a fraction year period of time. Unfortunately, it only worked for about 18 months before one of our devices in orbit failed, but Oxford still got all the data that they were looking for. One of the amusing side effects that we had was we built all of this in the US, and because ESA was our partner, we went out to Oxford University for 6 months to test it. There were 17 of the Lockheed Martin American people. We went there. When we actually started on the first day, a security guard comes by after about 5 o'clock in the evening. And for this test, which we have to run 24/7 to simulate the conditions of space, a thermal vacuum test, they told us that, well, we couldn't be here. They said, well, we have authorization, and we showed them the cards we had from Oxford. No, you don't understand. The fire department has gone on strike, and nobody can be in our buildings after 5 p.m. Well, of course, this was going to be a major problem for us since we had to be there for the next 6 months doing this test. So our manager comes over and talks with the security guard. And so 17 Americans got drafted into the Oxford Fire Department, where we would go around every hour listening for alarms and smelling for smoke, because if an alarm had gone off, there was nobody in the fire department there, so we had to call emergency services. So we wound up, as a side effect, joining the Oxford Fire Department for 6 months. Let's see, where are we in time? Okay, we'll at least go through this one and then maybe stop for some. I still have more slides after this, but we'll stop for some questions, see what people have to, if there's anything, and if we have time after the questions, I'll continue after this. SPADIS was a space dust detector that we worked with the Enrico Fermi Institute at the University of Chicago. It was on a grant from NASA instead of a direct project from NASA. The idea was to look for debris dust, interplanetary dust, natural dust streams, both in orbit, coming down from orbit to the Earth, and coming up from the Earth. You can see on the left-hand side, there's these 16 pieces of, the best way to describe it is charged saran wrap. Essentially, if a piece of dust pierced one of these sensors, it would produce an electric charge pretty in in line with the size of the piece of dust. So the bigger the piece of dust was, the bigger charge we had. So there was a front set of these 16 panels, and then about a half-meter space, and then a back set of these 16 panels. And so with that, not only could we tell the intensity of a piece of dust, but if it hit in the same plane on the front panel and on the back panel, we knew it was in orbit. If it hit at a higher plane on the front panel than the back panel, was going down, and reverse coming up. So we developed this. We gave it to the university to go in and launch, and it was 850 kilometers up in low Earth orbit. There were a total of 366 impacts they had over 260 days, but there was an oddity that happened across days 95 to 92, where, as you can see, we were getting 3 to 5 average per day. I mean, there were a few that went up to 9, but then suddenly it tripled for some reason that at the time we didn't know what it was. And the Enrico Fermi Institute calls us in and said, is there something wrong? And we go in, we look at the data, and we see, no, these impacts seem to be correct. And so we started doing some calls around to figure out what could have happened in orbit that suddenly caused all of these other effects. Well, it turned out the Chinese had launched one of their Long March rockets up into space, and it didn't go where it was supposed to go, and they didn't want it, hitting, the U.S. or Russia or anywhere else, so they decided to blow it up in space, figuring nobody would know. Well, we happen to have this dust detector for scientific purposes that was up there, and it turned from a non-incident, unfortunately, into an international incident. But as you can see, there was the initial 7 days, and then a few weeks later there was a little bit more, and then it calmed back down to normal. So sometimes a science instrument creates an international incident for no fault of our own. Should we stop briefly for questions, and then I can go back with what's the rest of the presentation if there's nothing else?
Sure, we have several questions.
Okay.
First one, roughly what angular deviation is there, plus or minus 100 miles, or orbit positional variation at GEO results?
At GEO? Back
GEO,
up.
okay, sorry.
Yeah, back up here. You mean in degrees?
Uh,
I think
This is
out here we
Matthew
had.
Thompson. Do you want to, let me see if I can find
Yeah,
you and allow you to unmute. You can explain that.
I believe it's 0.2 of an arc second.
Okay. Let me, okay, if you want to unmute and define that a little better, Matthew, I just allowed you to unmute.
That was the answer to the question. Thank you very much.
Okay.
Thank you. And we have, what's going to happen to tornado warnings once NOAA funding has been reduced?
So a lot of this is automated, and most of it is actually the responsibility of the local weather forecasters. So the raw data, I'm just trying to get back to that slide. The raw data will still be there. Come on.
What will be
the raw data will still be available, but it will land much more on the heads of the local weather forecasters to do this instead of NOAA itself.
That makes sense. And what will the reduced EPA do with the data now?
You mean the Environmental Protection Agency? Which EPA?
Yeah. EPA, Environmental Protection Agency.
Well, again, the data is still available. All the data collected from GOES is available to the public on a what's called CLASS website. So it can be the raw level 0 data and the processed level 2 data is available if people want to do their own analysis, without the government involved, on their own time and on their own funding. We actually do a lot of work with MIT. Pete Armstrong over at MIT he's the one of our primary end users in our interface on actually the new satellites out there. He had has a lot of the recommendations for that. So it will turn a lot more to the public than the EPA, NOAA, or the National Weather Service. And of course the local weather forecasters.
This is actually a multiple part question, so I'm going to split it up. The first part is, how crowded is it getting at geosynchronous orbit?
So geosynchronous orbit only allows 3,600 satellites to go in. The image that they always try to put into our mind is whenever we have to put something else in geosync, it's the equivalent of trying to take a helicopter that has a train car with a train running at 10,000 miles per hour without hitting the car in front of it or the car behind it. So every 1/10 of a degree, they allow one satellite in. So there are only 3,600 positions. And that I don't believe is ever going to change. I believe all of the positions, aside from, you'd have to check Wikipedia for the latest numbers, but I think it's under 14, have been used, and all the rest are allocated for missions for the next 15 years. So essentially, we're full. If that's the question itself.
So that feeds right into the second part of this question. Who regulates what satellites get to be there?
I personally don't know that. There is an international consortium that has decided that. But unfortunately, that's beyond where I build the instrumentation. I'm not actually involved in the decisions and such. That would be somebody else's question, but I'm sure you can find that on Wikipedia. I know it's an international consortium, but that's all that I can tell you.
And still the same question. Are satellite owners required to have a decommissioning process so there is mitigation of clutter at these orbits?
Yes. So ever since 1977, every single satellite in LEO and GEO, but obviously not ones that escape the Earth's atmosphere, are required to have a completely independent deorbiting system essentially stuck onto the side of it. That system has to have its own fuel, its own communication array, its own navigation system. and they essentially will come on if the satellite is intentionally decommissioned or in and of itself becomes defunct for some reason. And there's a splash area in the Pacific Ocean. I believe it's about 10 miles by 10 miles. There's no flight path. There's no whale migrations. There's no boat routes or anything over it. It's where they crashed the Mirror way back when, for those of you old enough to remember it. But yes, every single satellite is required to have a completely independent deorbiting system. Now, that's wonderful for everything since 1977. The problem is there's a lot of junk that was up there before 1977. Old used boosters and some other satellites that unfortunately are still there and drifting and are have no control. Eventually they'll fall down, but the question is, what do they hit in the meantime? The ISS has had to do dodges of many of these things over the years. There's talk about, for example, launching a satellite that has a bunch of these deorbiting things that we can go in and slap onto the side of the old stuff, but there's international problems with that. Would the U.S. trust the Chinese to do that? Would the Russians trust the U.S. To do that, to decide what is and isn't defunct? So while there have been discussions for deorbiting the old stuff, there's no solution, and that's only the big things. The small little bits and pieces that paint chunks and pieces of screws or entire screws themselves that are up there are a lot harder. I've heard jokes ever since the 1990s of, let's put a 5-mile thick sponge up there to catch this small debris, but I don't think I've actually heard any practical solution for the smaller stuff.
I think we're going back to one of your first slides. Was the LIM sounder payload also capable of imaging carbon dioxide distribution throughout the atmosphere? Yes. And if so, were any discoveries made related to atmospheric CO2 accumulation?
The answer is yes, but we don't actually get the... Let me go to that slide. Hang on. Whoops, here it is. The fun part of doing all this work is we go in and we build these things. And the reason we have partner universities is because they have cheap labor known as grad students to do the work and publish the papers. I know that the data is out there. If you go and look for the Hurdles final report, I know it's available online, but because we only built the satellite, we don't get to do any of the fun science out there. You'll need to find it from Oxford University or the University of Colorado's website. I don't think I've seen it personally, so it should be there somewhere.
Okay.
When you were discussing the phenomenology just before touchdown of significant tornadoes, you said that the inner cloud strikes dropped precipitously. I was wondering if you happen to know what that was attributable to.
You mean what atmospheric phenomena? Let me get back to the picture. Yeah, man.
Yeah, basically the red
this one
accumulated.
You want to know why it drops like this?
Yeah, I was wondering if they were able to identify why that is.
It's essentially because as the tornado is forming, what happens is there's a spinning in the atmosphere, so it actually the reason lightning strikes happen is inside a cloud. You essentially, the cloud is essentially water vapor that, as it gets compressed, it will make essentially what we'll call a droplet. What a droplet is it's not exactly a drop of water. It is water, but it actually winds up to have a lower density than the cloud itself. So once one of these droplets forms, it's not strong enough to be affected by gravity, but it will get pushed up to the top of the cloud as these things form. And essentially little droplets will dance on the top of the cloud, and eventually they'll hit other droplets and form something big enough to actually be a drop, which can be affected by gravity and fall down. So the charge that lightning has is, as these small droplets go up and the big drops go down, they actually transfer a charge into the cloud. Eventually, this cloud gets its own charge, and the cloud next to it has a completely different charge. And at some point, you're going to get a cloud to cloud. You'll first get intercloud changes, because it'll happen if the cloud's big enough. It'll happen on the left side of the cloud different than the right side of the cloud, and that's with the intercloud lightning. Then you have the cloud to cloud lightning, because this cloud now has a higher potential or a lower potential, whichever way it goes, than the other cloud, and they'll go between them. Once the tornado starts to form, it actually disrupts the cloud because it starts spinning around and changing the density of the cloud. So you don't actually get as much formation of these droplets, and that's why the frequency goes down. And then, of course, as the cloud completely spins at the top, when the tornado fully forms, that's what causes the very precipitous drop.
Okay, and now that I understand the mechanism, is there any way to use those data live from an imaging standpoint to identify potential touchdown sites with any accuracy?
Optically, you could potentially tell once it starts spinning. Of course, the problem is once it starts spinning, it's the tornado is really going to form within 5 to 10 minutes, and it's probably too late to even issue a. You can issue the tornado is going to hit right now, but you can't really give a warning ahead of time, and that's why we try to use the lightning to give the warning ahead of hopefully a pre-warning ahead of time versus the final warning of, oh my God, a tornado's right over there.
I was wondering if the magnetotail gave any better protection for NRHL orbits in a Sun-Earth system at L2 versus Earth-Moon.
Yes, it does. So, for example, if you're in the same orbit and you're in the this front area, the bow shock, versus being in the geotail in here, yes, L2 would be better protected than L1. L1 is actually completely outside. L1's about 1/100th of the way between the Earth and the Sun, so there's actually very little protection in L1 versus L2. L2 does give you much better protection.
Thank you.
From at least solar wind. Okay, so another project that we did, which was specifically designed just to look at the sun as opposed to the others, was the Solar Dynamics Observatory, which is still working, and in fact is currently planned to continue to still be working until 2030. So this one was actually a predecessor to SUVI. This one, though, looks in 10 different frequencies instead of the 6 that SUVI has. And we actually had 2 of the 3 instruments that were built on SDO. One of them was called the Heliomagnetic Observer, and that one was essentially measuring the sun's ever-twisting magnetic fields, which those are essentially what cause these big loops as they happen. Essentially, the loop is a large magnetic loop that essentially is drawing the sun's plasma up and around. And the CME happens essentially when this loop goes and twists itself. As they say in Ghostbusters, don't cross the streams. Well, when this magnetic field twists itself enough that the left-hand side of this hits the right-hand side of this, it essentially will blow off the entire top of this loop. And if it's pointed at Earth, that could be very, very bad. If it's pointed somewhere away, then you get the effects that you saw before. But this was all part of NASA's Living with the Star program. You can find plenty of images on YouTube. They have, for example, 10 years of sun, I believe is one of them. If you want to do a YouTube search, you can look at all of the data. that they've collected all the images, at least at one of the 10 frequencies, and a 10-year run. I don't know if they've ever did a 20-year one, but it's all available with um, on YouTube. Now, of course, one of the fun parts on this project is when they were doing the final closeouts before they launched it, they have toolkits essentially that they use inside the clean rooms that have a shadow box, so you can see if any tools are missing. Well, at one point, a flashlight about 6 days before we had to deliver went missing from the shadow box. So there may or may not be it could be that one of the technicians just didn't notice and stuck it in his pocket and took it home, or there may be a flashlight sitting in this in space thing, but it hasn't at least caused any damage. So we're happy. So this is a better view of what happens in a coronal mass ejection. And these are 4 of the frequencies. I believe this one's the 335. This is 171. This is 131, and this is 304 angstroms. And these are a combination picture from the SDO and then 2 other experiments. Stereo was another one where they had 2 satellites that were essentially being able to see these items in 3D, and Soho, which was a Japanese satellite. So these are combined pictures in those 4 frequencies taken by a combination of all of those. And I mean, you can see, for example, this large white spot in these 3 intensities becomes a slightly dimmer one here and is not here. So that's the reason that we have all of the different frequencies. We can see the same event looking at a bunch of different reasons. And these images are taken every 15 minutes.
While you're still on this slide, what is each frequency looking at?
Some of them are looking at, again, science is, I don't deal with the science as much. They just have it, they just have the information on us. I don't know, again, precisely what each of those are specifically trying to find, but again, Wikipedia can pretty quickly tell you what each of these wavelengths is looking for, especially for solar work. The one thing is, to build these guys, we don't actually need to know the science. We just need to know the engineering that has to go behind it. So unfortunately, I am not a scientist. One of the first ones that I worked on out of college, which is why the graphics look like they were done by a 3-year-old, was SEP-CPAD. This one was actually looking at energetic particles traveling along those magnetic field lines that you saw. Since it was LEO, we were actually crossing all of the magnetic field lines, both on the bow shock and on the geotail, and through the Van Allen radiation belts, which we were looking for high energy electrons and high energy protons. We had separate detectors for those along the magnetic field line. This was actually funded by the Max Planck Institute and Los Alamos National Labs out here. This one probably had the largest number of ground failures of any instrument I've ever worked on in there. The thermal vacuum chamber that we were testing this in nearly imploded. Essentially, there was a 50-foot chamber out in Hightstown, New Jersey, and a liquid nitrogen leak essentially ripped a 25-foot chunk of 1.5-inch thick steel off of the chamber. The people who were in front of the chamber at the time, we were off in another room, so we didn't hear this, said it sounded like a truck hit the chamber. They essentially ran to the back of the chamber and saw liquid nitrogen pouring across the floor, humidity condensing on all of the electrical panels, and of course, then the low oxygen alarms go off, and they evacuated the building, because if that 50-foot chamber had imploded, it probably would have taken the building with it. Fortunately, it just it only caused the problem on that rip. They essentially went in, were able to walk in there with ceramic shoes and a scuba suit to turn off the liquid nitrogen. They brought out Chicago bridge and iron that had built the thing. They came out with welding rods that were about 2 inches in diameter, sealed up the crack. They did an MRI of the chamber, and we were able to restart about 4 days later. But that one was interesting. There was also a magnetometer, because we were supposed to be measuring all of the values on the magnetic field. There was a magnetometer on the ground that, because they had flown so many of these, they didn't actually send any representatives with us. And nobody actually noticed on the ground when they moved it from California to New Jersey that the magnetic field didn't change. And so they launched it, it turned out, with a bad magnetometer. So instead of being able to directly find where these magnetic fields were, after they launched it, I had about 3 weeks before we became active to rewrite all of our code to turn us into an imager so we could find the magnetic field first and then do our detection. But it was very interesting as it went through. So
we have AJ Coco. You have a question?
For this enlightening presentation, from the overwhelming effect of the sun to the Oxford Fire Department anecdote, it was fascinating. I do have a question, though. Do you have any optimism at all that the 90% plus preponderance of the sun that message will reach the global warming / climate change / anthropomorphic community?
Again, I'm not on the science side, but it would be nice if it did. I mean, the only thing we can do is present these things and let the community decide how they wish to proceed. Whether, I mean, that it may not be the U.S. for at least some period of time that continues that. It may have to wind up falling on European allies and others in the short term, and who knows what will happen in the long term.
Well, it seemed to have quieted down somewhat in the recent past.
Yes. Now, again, part of it is not actually due to man-made. I mean, there were, for example, there was a mini ice age. I believe it was 1350. That wasn't caused by man. That was just caused by natural phenomena in the sun out there. So you can get effects both natural and man-made. Mm-hmm. And there's not much we can do about the natural ones.
Anthropomorphic argument kind of fell down when the gas concentration above the poles, where there is no manufacturing, seemed to be greater than expected.
Yes, and that was actually one of the reasons we launched that Hurdles instrument, was to record, because at that we essentially launched it at the point they were phasing out chlorofluorocarbons, and the idea was actually to measure the recovery. Since we had both the CFC and the aerosol detectors on there, was to measure the recovery of the Earth as it went in, and they did actually see a significant recovery once CFCs were phased out. So mankind definitely can have an effect on some of these items, just not necessarily all of them.
Like
but
less than 10%.
We need we need the data to be able to even make those arguments.
Okay. Well, thank you for that.
Yep.
Here. So Christopher Santos, is the mission length primarily limited by fuel capacity, and what happens to a craft after mission ends?
That's where we deorbit using the completely independent. So, as I said, that's why it has to have its own fuel supply, its own navigation, its own control computer. Whether it dies naturally, because we got to the end of the mission, or whether it just abruptly dies because it got hit by a again, one of those screws we were talking about there, or it overloads its power supply or whatever. That was the reason that the whole deorbiting system has to be completely independent.
Bill had several questions. I think about the 10-year satellite replacement interval. How much of that is because the lost redundancy is expected to fail, and how much is obsolescence of the current satellite?
So for example, on these GOES missions, they were planned for 5 years of on-orbit storage, which might happen before you make them active or might happen after you bring them up, and 10 years of life. We have a requirement that's handed down to us from NASA that says you'll have a 0.6 reliability, so a 60% chance that with a primary side and with a backup side in there, it will last for the 10 years of operation and 5 years there. Almost all the time we exceed that, typically by a factor of 3. Out here, none of these GOES instruments, for example, even the ones, the oldest ones that we've had out there, we never even had to go to the backup side, and we leave them in storage. So, for example, now that we're running 18 and 19, we still have 16 and 17 sitting in storage. That if something happened tomorrow and GOES 19 just failed, and we had to deorbit them, we could bring back one of the other ones in. It would take about a week's time to reposition it and turn it on again and bring it up. So even if it didn't meet its life, we also have the old ones as a backup. And again, as we get the new series in the 2030s brought in, we'll take out the older and older ones, but we always can bring it back up if there's an issue. And so far, as I said, we've never had a failure. Most of our missions, like that are supposed to last for 3 years, assuming it doesn't have a consumable, Gravity Probe B, they only had 18 months of coolant, and it lasted the 18 months. But most of these other things can actually last significantly longer than what they're designed for.
This one from Dan Durham. What causes the dip at the top center of Zone 4 on the tornado risk map?
Tornado risk map.
Yeah,
I don't think I'll be able to answer that question, but hang on, let me get back there. Almost there. Yeah, man. There it is. So the question was the depth of what? The clouds?
I'm sorry, let me go back to it. I was looking ahead at another one. Scroll down here. It was Dan Durham, wasn't it? I mean, it seems to have fallen off now. I could get him on. Yeah, there it is. Nope, wrong one. I'll find it again.
Okay. But fundamentally, it doesn't have to do with cloud depth. It has to do with how strong the winds are likely to be, and that will change what the intensity of the tornado could be, based on whether or not you're near. As you can see, if you're near water, you're actually likely to be a little bit warmer and not be able to develop as strong a wind as you can in this stage 4 zone that you were talking about before.
Yeah, I did find the question. It is Dan. Let me unmute you for a second if I can find you. Does that answer your question? Here you go. I'm going to unmute you. Oh, Dan. Okay, I'm going to assume that answered the question.
Just as a note, there have been really silly proposals. One of which was to put half-mile wide walls going diagonally across the country in 3 places. I don't know who would want to live next to stop these tornadoes completely, because of course, if it doesn't have access to the lower level winds, you won't get a tornado. Yeah, that might work, but ridiculously impractical, and I don't know who would possibly pay for it. But there have been very silly scientific proposals that we've heard in our views here.
We have a couple more here. Matthew has another one. Was any significant weather phenomena similarly attributed to, I think that's one of the older ones. No, okay. I think we did all these. Yeah, he just had another note in there. I think I've got everybody now, so if I haven't, go ahead and raise your hand and I will unmute you.
I'm still trying to get back to where we were. These are just some backup slides I had. This is what we were talking about before, where you have charges within the cloud. So essentially, this is where you get the small little droplets forming a charge, and then as I said, if the droplets go up and the drops go down, you'll actually get separation. So this is where you can get cloud to cloud lightning, cloud to ground lightning, and very rarely you can get cloud to air lightning as it comes in. But tornadoes actually form on the ground initially, and they'll essentially make this circular pattern if you have warm, dry air and cold, moist air. You'll essentially start on the ground, and winds going in two separate directions. You'll start getting, from the ground level winds and the higher level winds, you'll start getting this spinning, and then the spinning will cause the updraft, which will eventually cause the tornado out here. But once this updraft happens, this is where what we were talking about before. The clouds themselves start dissipating, and you won't get as much lightning as happened before. So you can find this on NOAA's website, all about what causes the tornado and what causes the lightning and hail and everything else. Let's see, what else do I have in here? Oh yeah, and then for the more scientifically interested people, what we're actually looking at when we're looking at lightning is we're not looking at the bright flash itself. We're actually looking at what happens before the bright flash. So, granted, we only see it a few milliseconds before the actual flash, but what we're looking at is 777.4 nanometers. And what happens at that point is you have, this is an oxygen singlet on the right-hand side. Normally you have these two electrons that share across one oxygen to another as it goes in. When you get a huge magnetic field, it turns out that oxygens get kind of torn apart into these oxygen triplets, and something happens that would never actually happen in nature. Normally, when you have one electron going this way, you get one going the opposite of this way, and nature loves balance. It turns out in these huge magnetic fields, you can actually get the extra electron spinning on this oxygen and on this oxygen in the same direction. So this essentially has a net charge on it. This puts out a very specific frequency, which can be read at its peak on 777.4, and we can see that through water vapor, which is one reason we can see that through the clouds as they go in. So it goes from this to this as the magnetic field forms in what is going to be the tube where the lightning flash is going to happen. So that's why I'm saying it actually pre-stages the lightning flash itself, and just again, it's just past where we can see. So the human eye can see it about 750, where we're out here. But when the lightning flash actually happens, the magnetic tube collapses very, very quickly, and that collapse of going from this to this some of these oxygens aren't going to nicely just turn back into oxygen singlets. They're going to get ripped apart, and the free oxygen, the free electrons, will get released, and that's part of what causes the flash. Also, as these things get ripped apart, you essentially have a violent motion in the air, and that's what causes the thunder that accompanies the lightning flash. So that's just a little bit more scientific background for those who want to see that. Let's see, what was my last slide? This was just credits.
Bill says he does have a question, so I'm going to ask him to unmute. And go ahead, Bill.
I had to move my mouse pointer. For the Hurdles mission, what is LIM?
What's a LIM sounder? So it's essentially the plane of the satellite motion. So that's why when we look at it, we look at the Earth's. Essentially, if you're looking at the rear view of your car, if it's going forward, you look out the back window. Pretend you could see the curvature of the Earth. That curvature as it falls down, that's the limb. And obviously from space, it's much easier to see the curve than it is from the ground, but it should give you the idea. So you're looking out the limb of the Earth, and that's what we're scanning through. When we start at deep space, you essentially look straight, and then you start going down as the Earth's atmosphere is there. Again, hit the Earth and then scan back upward. So that's what we mean by limb.
Oh, thank you.
As far as I know, that's all the questions right now.
Okay. So. Well, and that's all of my presentation. So.
Okay. Well, thank you very much. This has been a great presentation, and I think everybody got a lot out of it. So, thank you.